Good morning. Finally, the last lesson of the course. How do we figure out an optimal strategy in a two-persons game? So, as usual, this is best done with an example. There is actually a nice formula. I could just basically finish, in fact, this class in 2 minutes by simply writing down the formula for the optimal strategy, but it's nice to know where it comes from and why there is such a thing as an optimal strategy. I think that's very useful to understand the whole logic behind it. In practice, when you go over the problem, just apply the formula which is given in the formula sheet, and we'll put it on the paper here as well. So suppose that the payoff matrix for a game is A equals 3 minus 2 minus 1 and 2. And by the way, notice that this is not strictly determined game. Remember, if it's strictly determined, things are not that interesting, right? I mean, the strategy is always to use one row or one column, right? If you want to minimize or maximize the loss, or to maximize the payoff if it's positive. So and this is because there is no element which is the least on its row and a maximum on its column, right? So that's not a strictly determined game. So let's say, suppose you're player one. So let's focus on player one, who will choose the rows, right? And remember, the frequency of choosing the two rows typically is denoted by P1, P2. But remember that the two should add up to 1. So for the purpose of this lesson, let's actually call the first entry P and the other one 1 minus P. Because they always add up to 1, and it's going to be easier to make the point what goes on if you want to choose the optimal strategy. You just have fewer variables. Right, so P1 plus P2 equals 1, so you might as well call one of them P and the other one 1 minus P. All right, so the player one deals with two possible expected values. Expected value, call it E1, which is in response, which happens if the opponent will choose column 1. Okay, so the opponent will choose column 1. In that case, the payoff will be $3 times P plus minus 1 times 1 minus P. Right, so you either get $3 with probability P, or you lose $1 with probability 1 minus P, because that's how the player chooses the probabilities for the row 1 and row 2. So you can think of E1 basically as a linear equation in P, right? So that's going to be 3P minus 1 plus P. Let's do this computation. So that means, let's write it on here from the beginning. E1 is going to be 4P minus 1. All right, so that's one possibility. The other possibility is the expected value E2, which is in response from the opponent choosing column 2. If the opponent chooses column 2, then of course the payoff is now minus 2 times P, so a loss of minus $2, or a gain of $2 with probability 1 minus P. Again, doing a little bit of computation here, this is minus 2P plus 2 minus 2P. The second possible expected value is going to be 2 minus 4P. Keep in mind, we call them E1 and E2 because they happen if the opponent will choose column 1 or column 2. All right, so let's graph these expectation. With respect to P. So as linear functions of P, right? So we're going to do this on the left side. And keep in mind that the domain, on the P axis, so the horizontal axis will be given by P. The domain there is 0 and 1, right? Because as with any probability, the value should be between 0 and 1. The expected value can be any number, right? But it's going to be 0 or 1 for the probability P. So let's plot these lines. Let's look at E1. We're going to write down a couple of coordinates for E1, right? So if P is 0, let's plug in 0 and 1, in fact, right? So if P is 0, the value of E1 is going to be -1. That's going to be the Y coordinate, basically. And if P is 1, the value of E1 will be 3. So 0 minus 1, let's say this is -1 over here. And then 1 and 3. Well, actually, let's exaggerate a little bit, because then it's going to look weird. So let's say this is -1. And I hope it's, well, I'll have to figure out how to make it, because we'll have to basically scale down a little bit this one. And then 1 and 3. So let's say P equals 1 is here and 3 is over here. Okay, so this is basically the line which indicates the expected value E1, depending again on which P you choose, right? So the question for player 1 is, what should P equal to? So I know what is the distribution, I mean, what's the strategy I have to employ, so that I can get as big as an expectation value as I want. Okay, but what if the opponent chooses the other column too? Let's plot that as well. So if P is 0, the E2, the Y coordinate is going to be 2. And if P is 1, the coordinate, the E coordinate is -2, right? So it's going to be 0 and 2. 2 is over here, maybe. And then if P equals 1, that's going to be -2. So E2 will be like that. All right. So this is the key thing. How do we figure out the optimal strategy? Imagine you're player 1, right? So you want to get as big a value as possible, independent of what the other player does. So for example, look at this intersection point, right? And imagine you're going to choose a p-value to the left of it. So maybe you choose the p-value here. Now, you're going to hope that the player 2 will choose column 2 so that the payoff ends up being on E2 line. But in the long run, the opponent might figure out that your strategy is biased toward that choice, and for sure he's going to choose E1 and you're going to start losing money. Okay, so you will definitely want to be here, or I put this little circle, which means you will definitely want your opponent to choose column 2, but the opponent may catch the trick and is going to basically choose the other column, and you will end up with a loss. Okay, then you're going to say, what if I'm going to choose a value to the right of the intersection point? Well, you'll definitely hope in this case that your opponent will choose now column 1, because you'll definitely want the big prize. You want the point over there. But your opponent may figure out your strategy, and instead your opponent will choose the opposite column, and you're going to lose money. So there is basically this intersection point, the sweet spot in between, in which no matter what the opponent does, that won't affect your payoff. So the optimal strategy is given by the intersection point, because it is not affected by opponent choices. Now, it's important to understand that's not like this is the possible outcome. If you think your opponent is silly enough to choose column 2, you can choose a probability distribution close to 1, so you can get, the big payoff over there. But if you want a strategy to be independent of your opponents, who might be just as smart as you, then you want to be at the intersection point, because that's the one that doesn't depend on the choices of the opponent. So I hope that's clear, why the intersection point is going to be the best outcome. So how do you find the intersection point? Well, you set the two expected values equal to each other. So that means for p minus 1 is equal to 2 minus 4p. Move the terms around. 4p plus 4p equals 1 plus 2. 8p equals 3. P equals 3 over 8. And automatically 1 minus p will be 1 minus 3 over 8, which is 5 over 8. So the optimal strategy for player 1 will be 3 over 8, 5 over 8. And guess what? We're gonna go a little bit faster this time around, so that, because I hope the idea is pretty obvious. The same discussion works from the point of view of the second player, right? So let's denote the strategy of the second player to be q1 minus q. And then this player also has two possible expectations. E1, if the row 1 is chosen, well, that's going to be either $3. So look at look at the two possible entries corresponding to row 1 and row 2 from the payoff matrix. So $3 times the probability q plus minus $1 with probability 1 minus q. So that gives me $3, 3 minus 2 minus 1, 2. Player 1 will choose column 1. If row 1, the entries are 3 minus 2, right? Yeah, because the player 2 will choose either column 1 or column 2 with probabilities q and 1 minus q. And of course, if the opponent chooses row 1, then the entries are 3 and minus 2. So that gives you 5q minus 2. Furthermore, if the opponent, the player 1, chooses row 2, then the possible payoffs are minus 1 and 2. So minus 1 with probability q, $2 with probability 1 minus q. This is going to be 2 minus 3q. Again, if you plot the situation, it's going to be very similar. So let's see if I can do it here. So E1 equals 5q minus 2. Let's plug in 2 points here. So q equals 0. That gives me E minus 2. And if q equals 1, because it has to be between 0 and 1, right? As with any probability. So if q is 1, the expectation E1 is equal to 3. So I have 0 minus 2. Let's say this is minus 2 over here. And then 1 and 3 over here. I think it's going to be a little bit squished here. But anyway, this is the expectation 1, the expected value 1. And let's say E2, which is 2 minus 3q. Possible points are 0 and 2. And if q equals 1, E2 is minus 1. So q equals 0 and 2. It's going to be here. And then q equals 1 and minus 1 is over here. And that's E2. So once again, the optimal strategy will be at the intersection of 2 points, because that's the one that doesn't depend on the choices of the opponent. So it's basically when E1 is equal to E2, and that means 5q minus 2 equals 2 minus 3q. Move the terms. 5q plus 3q. 2 plus 2, 8q equals 4, and that gives me q equals 1/2. And obviously 1 minus q is 1/2 as well. So the optimal strategy for the second player is to choose the two columns equally likely, 1/2, 1/2, or just as often, 50-50. Okay, so the good news is that we can actually come up with a formula so that we don't have to write these graphs, but I hope it's clear why there is such a thing as an optimal strategy. On the second page, I'm going to write out the value of the game with optimal strategies. We're gonna state the formulas and finish up with another example using those formulas. So stay tuned for the last page. Okay, so the last thing to do, of course, is to figure out the value of the game at optimal strategy, right? So once you find the optimal strategies of the two players, then the last question possible is the value of the game played at optimal strategies. So if the game is played repeatedly and both players employ optimal strategies, then what's going to be the value of the game? Is going to be favoring one or the other. So that's P times A times Q. Remember, it's the same formula as before, except now P and Q are not just any strategies, but are the optimal ones. You may have to use the calculators for this one. Well, maybe not, I guess. Let's do it in exact format. So that's going to be, let's see, the first multiplication is going to be 9 over 8, 3 over 8 times 3, right? So that's going to be 9 over 8 minus 5 over 8 minus 6 over 8 plus 10 over 8 multiplied by 1/2, 1/2. That's 4 over 8 comma 4 over 8, which is actually 1/2, 1/2. And that gives me 4 over 16 plus 4 over 16, 8 over 16, that's 1/2. That favors player 1, right? Because it's a positive. So if they play basically their best strategies, the best player 1 can do is to gain $1/2. The best player 2 can do is to minimize this loss of $1/2, right? Just as before. So we're going to have a nice formula for all of these in terms of the entries of the payoff matrix. We're not going to prove this formula. It's not that difficult, but it's essentially writing all the computations you've seen in this section, but without with variables instead of numbers for the payoff matrix. So instead, we're going to just state the formulas, and then we're going to write down just an example, another example before we call it a day. So let's say the payoff matrix is equal to A11, A12, A21, A22. So that's basically the typical notation of the entries of a 2x2 matrix. So the formulas are like that. Optimal strategy for player 1, denoted by P1, P2. Optimal strategy for player 2. You can actually skip writing this because you have it in the formula sheet. Q1 and Q2. Well, my students, because I'm thinking now that months or years after that, there will be maybe other people who watch this who didn't have the formula sheet. So the optimal strategy for player 2 is Q1 and Q2. And the formulas are as follows. So for P1, that's equal to A22 minus A21 over A11 plus A22 minus A12 minus A21. This comes from solving those intersection points, basically. P2 will be A11 minus A12 over A11 plus A22 minus A12 minus A21. Then the formulas for Q1, that's going to be A22 minus A12 The denominator basically is the same if you noticed, right? So A11 plus A22 minus A12 minus A21. And let's see if I can squeeze this in here. Q2 will be A11 minus A21 over A11 plus A22 minus A12 minus A21. Right, denominator is the same. And then finally there is a formula so that you can save time as well. The formula for the payoff, the value of the game at optimal strategy. Let's call it E, right, which is PAQ. And then in terms of the original entries, the payoff are A11, A22, minus A12, A21. Maybe I should actually write ABCD next time. A11 plus A22 minus A12 minus A21. Okay, so with these formulas, basically, once you have a payoff matrix, let's write an example. Well, in fact, let's write two quick examples. So the previous example, just to see you get the same values, but with the formulas directly. First thing to do is to write down what each of them is equal to in the formula, right? So if this is the matrix, then A11 is equal to 3, A12 is minus 2, A21 is equal to minus 1, A22 equals 2. So P1, follow now the formula, right? A22, that's 2 minus negative 1. You have to pay attention to those double negatives, right? Because A21 is minus 1, and the denominator is 3 plus 2 minus negative 2 minus negative 1. And remember, the denominator is the same, which in this case is going to be 5 plus 3, which is 8. So from this point on, it's going to be faster, right? So P2 will be on the top A11, so that's 3 minus negative 2. Denominator is the same, so that's 5 over 8. Q1 is equal to 2 minus negative 2 over 8, which is 4 over 8, or 1/2. And Q2, 3 minus negative 1 over 8, which is another 1/2. So strategy for player 1, as we know already, 3 over 8, 5 over 8. Strategy for player 2, 1 over 2, 1 over 2. Optimal strategy, I mean. Expected payoff at optimal strategy, again, denominator is the same, 8. On the top, we have A11 times A22 minus A12, which is negative 2, A21, which is negative 1. 6 plus, no, minus 2, because it's minus, minus, minus. So 6 minus 2 over 8, 4 over 8, which is 1/2. So we can put one more in just for practice. You may have to use probably the calculator here. Actually, let's see, minus 2, 4, 3, I was gonna see if yeah, let's do another one. Yeah, so let's say another example, and then we can call it a day. So A, let's say the payoff matrix is minus 2, 4, 3 minus 1. Why don't you actually take 2 minutes to do it on your own? Maybe you should pause to just check to see if you can plug in these numbers correctly, and then continue the video and check with me. So the entries in the order are A11 minus 2, A12 4, 21 is 3, 22 is minus 1. So, okay, so let's do this example here. I was going to do it on a previous page, but there was a little error, so I had to cut the videos, the last part. So this is the payoff matrix and the entries -2, 4, 3, and -1. And for player 1, following up the formula, so just print out the formula sheet and look it up. So P1 is A22 minus A21, that's -1 minus 3, divided by A11, which is -2 minus 1 minus A12, which is -4, minus A21, which is -3. So that's going to be -4, and that's -10 here. So 4/10, which is 2/5. And remember, the second probability, P2, is adds up to 1, right? So P1 plus P2 is equal to 1. You don't actually have to write each expanded formula for each of them, because once you find one of them, the other one is 1 minus the first one, right? Because they add up to 1. So that's a little bit faster. 1 minus 2/5 is going to be 3/5. Okay, so therefore the optimal strategy for player 1 is 2/5, 3/5. And then let's move on to player 2. Again, in that case, you can compute just one of them. Let's say you compute Q1, which is A22 minus A12 on the top. So -1, -4. Denominator is the same as before, so that's going to be -5/10, -5/-10, which is 1/2. And then Q2 obviously is going to be 1/2 as well. So the optimal strategy for player 2 is going to be 1/2, 1/2. So let's do the expected value at optimal strategy. So that's going to be 2/5, 3/5, -2, 4, 3, -1, times 1/2, 1/2. So let's see, that's going to be -4/5 plus 9/5. Second is going to be 2/5 times 4, that's 8/5, minus 3/5 times 1/2 and 1/2. And that's going to be 9 minus 4 is 5/5, which is 1, right? So 1, 1 times 1/2, 1/2. So 1 times 1/2 plus 1 times 1/2 equals 1. So the optimal strategy is equal to 1. So the last remark I want to make, because that's also important, right? And let's actually write as a remark. Any deviation from optimal strategy gives obviously a worse outcome for that player, right? So because the value of the game is 1, that means any other strategy that player 1 will do, assuming player 2 continues to do his optimal strategy, is going to result in a worse outcome for that player. So basically, let's say player 2, let's change a little bit. Let's say player 1, I'm sorry, will use the strategy 1/3, 2/3, which is not optimal, right? And the second player will choose the optimal strategy 2/5, 3/5, let's say. And let's do the payoff again of the game. 1/3, 2/3, -2, 4, 3, -1. And the first product is going to be -2/3 plus 6/3, 4/3, -2/3, 2/5, 3/5, 4/3, 2/3, 2/5, 3/5, and that's going to be 8/15. 4 times 2 over 3 times 5 plus 6 over 15, 14 over 15, which is going to be 0.93, which is basically less than 1. Okay, so rational players essentially will have the interest, in this case, both of them, to play optimal strategy to get the best possible outcome. So I hope you enjoyed the class. I might add later on various topics, as I often do. Those will be probably additional topics which are not mandatory in the class, but for anybody who is interested in the topic can review them later on. And that's it for today and for the semester. Goodbye.